Alrighty guys, so this is our first lesson going virtual with this whole epidemic of the coronavirus. Hopefully it goes successful, and leave me a comment or email me with any suggestions you may have, alright? Let's get started though. So before we move forward and talking about any new material, I want to talk a little bit about what we've been learning so far. Just a small review. The first thing that we had mentioned about this section was non-polarity versus polar covalent bonds. We know that in order for a bond to be considered polar, there has to be an electronegativity difference of 0.5 or greater. Alright, and anything below 0.5 is considered to be non-polar, and everything above 2.0 in regards to the difference is an ionic bond. Alright, so remember that we use electronegativity values to determine polarity in a bond. The second thing I want to talk about is partial positive charges and partial negative charges. Keep in mind that the way we tell which atom has a partial charge is by looking at those electronegativity differences. For an example, whichever one has the greatest value is going to be partial negative because those electrons are spending more of their time around that atom with a higher electronegativity value. Electronegativity. Remember the definition for electronegativity. The definition for electronegativity is defined as the ability of an atom to pool on shared electrons. Alright? And this last part, 3 ways to demonstrate a polar covalent bond, was something that I asked you to do on your own. So let's get started with some new material. Okay. So now we've talked about polar covalent bonds. Let's talk a little bit about how polar covalent bonds make up polar covalent molecules. They're totally separate, two separate things. You can have a molecule that has polar bonds, but then that molecule can be nonpolar. Alright, so it's crucial that we understand that having a polar bond does not mean we have a polar molecule. Alright? The presence of a polar bond usually gives rise to a polar molecule. And that means that one end of the molecule is slightly negative and the other end is slightly positive. So when we thought about a polar bond, we thought of as one atom having a partial positive, one of the other atoms having a partial negative. We're going to see that same type of behavior with the molecule. Alright, this side of the molecule is going to be partial positive. This side of the molecule is going to be partial negative. Alright, polarity, is defined as having two separate charges. Polarity refers to having two poles, one side with a positive charge and one with a negative charge. Alright, so let's look at water for an example. Water H2O. Now notice that we have an oxygen and we have the two hydrogens situated in that orientation. I don't know if you can see, but the oxygen has partial negative charges that are affiliated with it. Alright, remember, oxygen is highly electronegative, so it's going to want to take more electrons. With that being said, it's going to obtain a partial negative charge. Since it has two hydrogens surrounding it, each one of those hydrogens is going to be electron deficient because they have a very low electronegative value. So the oxygen is taking a lot of those electrons. Remember, it's not stealing them. They're still sharing those electrons. It's still a covalent bond, but oxygen is going to pool on those electrons a lot stronger than the hydrogen. Therefore, we give those charges out accordingly. These arrows are showing that the electrons are attracted more to the oxygen. All right. This gives rise to a polar molecule. Now, instead of just having 4 separate partial charges, we only have 2. We have a partial negative at the top and a partial positive at the bottom. All right, partial negative because of that oxygen and partial positive because of these 2 hydrogens. Because we have those 2 poles, those 2 oppositely charged poles, you can think of it as like the North Pole and the South Pole. All right, on the Earth we have the North Pole, which is up top, the South Pole at the bottom. Alright, this is the same thing. We have a pole up here and we have a pole down here. But in this case, instead of north and south, we say this one's negatively charged and this is the positively charged pole. Alright? Alright. Next, a molecule that has 2 poles is called a dipolar molecule or a dipole. Alright, we're going to just use that word dipole. Anytime that we have a molecule that's considered to be polar, we say that it obtains a dipole. The water molecule is a dipole, right? In the case of water, which pole would be attracted to a positively charged plate and which would be attracted to a negatively charged plate? Yeah. Okay, so basically if you look at this water compound, if you look at that molecule, which end would be attracted to a positive plate, which would be attracted to a negative plate? I'll give you about a second to think of that. Okay, sweet. Electrostatic forces tell us that oppositely charged particles attract. So this end right here, the partial negative end, is going to be attracted to a positive plate. This positively charged partial charge down here is going to be attracted to a negative plate. All right, attracted to a positive plate, negative plate. That answers that last question. But, like I've mentioned already, so how do I want to say this? Remember, just because we have polar bonds does not mean we have a polar molecule. All right, and this is a prime example to show how that's the case. All right, we can have polar bonds, but that molecule, based off the shapes and based off the orientation of the atoms, can give rise to a non-polar compound. All right, and vice versa. All right. So the effect of polar bonds on the polarity of an entire molecule depends on 1, the shape of the molecule, and 2, the orientation of the polar bonds. All right, we'll get to that in detail. For an example, CO2. CO2 is comprised of 1 carbon, 2 oxygens. It has 2 polar bonds, but it has a linear shape. All right. If you look down here, notice that we have the electronegativity values for carbon and the electronegativity values for oxygen. Carbon has an electronegativity value of 2.5, oxygen 3.5. And remember, the way we find the whether the bond is polar or nonpolar is we take the difference. All right, the difference between these two values is 1.0. And keep in mind that if the difference of electronegativity values is 0.5 or greater, it's going to be polar. 1.0 is much greater than 0.5, therefore this is a polar bond. This right here is a polar bond. This right here is a polar bond. All right, so we have 2 polar bonds. We have one to the left and one to the right. But even though we have 2 polar bonds, CO2 is a non-polar compound. All right, remember, polar, greedy. We want electrons. Non-polar, not greedy. There's an equal distribution of electrons. All right. In this case, there is an equal distribution of electrons. All these atoms are sharing the electrons equally. There is no unequal distribution. This is all equal. All right. That's what it means to be non-polar. All right. The reason why it's non-polar, even though it has separate polar bonds, is because of the shape, the linear shape. Notice that it's a 180-degree molecule. That means that this oxygen is pulling on those shared electrons to the left, and this oxygen is pulling on those shared electrons to the right. Because they're both pulling at the same degree with the same strength, they're going to cancel each other's polarity out. This oxygen is going to cancel the polarity of this oxygen, and this oxygen cancels the polarity of this oxygen. Therefore, there's an equal distribution because they're both pulling to the left and to the right at an equal strength. All right. Even though there are 2 polar bonds, because of the linear shape, the bond polarities cancel because they are in opposite directions. It's like you have some, let's say that, I don't know, you have a weak individual in the middle, and then you have 2 very strong guys at the end. All right, and they're playing tug of war with this scrawny little kid. Both the extremely strong people on the end are going to pull the rope from the little guy at the same extent, to the point where no one's really winning. There isn't a greater pull to this side, there's not a greater pull to this side. They're equally pulling, even though that, this strong guy is a lot stronger than this little guy, this guy is a lot stronger than this little guy, they're pulling at the same extent. Therefore, it's non-polar. All right, you can circle that, non-polar. Let's look at another example. We have ammonia. Ammonia is 1 nitrogen and 3 hydrogens. We have 3 polar bonds. All right. I don't have the values here, but nitrogen has an electronegativity value of maybe 2.9, and then hydrogen around 2.1. So it's a difference of 0.9. All right, 0.9 is a large enough difference to consider that bond to be polar. All right, so this is the polar bond. This is a polar bond, and that's a polar bond. So notice if it's a polar bond, nitrogen having the largest electronegativity value, those electrons are going to be attracted upwards towards that nitrogen. Don't worry about these dots and this wedge. It's just showing the orientation, meaning it's showing that the hydrogen is actually going back and the hydrogen right here is coming out. All right, it's just a way to represent the molecule in a 3D fashion. All right, not important. All right, so we see that the electrons are being attracted upwards towards the nitrogen. So we can, at the right hand side, we can say that the net polarity is going upwards towards the nitrogen. All right, notice that there are no polar bonds that are canceling each other. In this case, they were canceling each other. Here, we notice that there's nothing going in opposition. We don't have one coming this way to cancel that one. We don't have one coming down this way to cancel that guy. And we do not have one coming that way to cancel this one. They're all going in a direction that they're not really experiencing any opposition. Therefore, we have a net polarity going towards the nitrogen. This is a polar bond. In this case, this guy's going to the left, but this guy's going to the right. So they're canceling out. Nothing is canceling out these hydrogens. Therefore, we have a polar bond. There is a dipole directed upwards. Okay? This is the assignment for today. All right? Notice in this assignment, so you have 1, 2, 3, you have 8 different molecules. All right? Each molecule has different atoms, and I want you to tell me whether that molecule is polar or non-polar. All right, and notice that in each example, I give you the electronegativity value for each atom. My advice to you: take the steps upwards to go along with this assignment. First thing you want to do is you want to assign each element with an electronegativity value. All right, I already did that for you. Okay. Next thing, you want to determine which element is higher in electronegativity value. All right, so I'm going to actually do an example, just one example, so that you can get a feel for what to do. All right, let's do number 3. All right, so the first thing we're going to do, assign each element with an electronegativity value. All right, in this case, I have carbon double bonded to carbon. I have a carbon bound to a hydrogen, carbon bound to a hydrogen, carbon bound to a hydrogen, and carbon bound to a fluorine. The first thing I want to do is I want to assign these carbons with a electronegativity value of 2.5. These hydrogens have an electronegativity value of 2.1. And the fluorine has an electronegativity value of 4.0. All right, that's step 2. Determine which element is higher. All right, we just did that. Number 3. We want to determine whether each bond, not molecule, each bond is polar or non-polar. So in this case, this bond right here, is that polar or non-polar? The bond between carbon and hydrogen. Well, this carbon is 2.5. This hydrogen, 2.1. And let's just go really back. Let's go back really quick to this. Okay, so anything below 0.5 is nonpolar. All right, with that being said, this bond is nonpolar. The bond shown here is nonpolar. This one's nonpolar. Carbon bound to itself, they both have the same electronegativity value. They're going to pool on those shared electrons with the same degree of strength. Nonpolar. And we have another carbon-hydrogen bond. Nonpolar. All right. We have 1, 2, 3, 4 nonpolar bonds. All right. Now let's look at the last bond. Carbon bound to fluorine. Fluorine has a electronegativity of 4.1. This carbon has one of 2.5. The difference is 1.5. 1.5 is large enough for there to be a unequal distribution of electrons. That bond is polar. All right, so let me rate. Well, I can keep that there. This bond is polar. And I'm using that arrow to show where those electrons are being attracted to the most. They're being attracted more to the fluorine. So this is showing that there's a polar bond with those shared electrons being attracted to the fluorine. Alright, this is a polar bond. Everything else is non-polar. Do we see anything canceling out? Does the geometry matter? Alright, do we have any cancellations? And just looking at this, we have no cancellations because everything is non-polar. The only thing we have polar is this bond here. Therefore, this is a polar. This is polar. Polar because we have one dipole moment. We have one dipole, and it's going towards the fluorine. Nothing canceling out. Geometry doesn't matter. We use an arrow to define the polarity. This is polar. All right, I want you to do that for all the other examples. I will put the answers up not shortly, but as soon as I get everyone's assignment. All right. So yeah, leave a comment if you have any questions or you're concerned or anything like that. All right, guys. That's about it for today. All right. So that is our first video. I hope you enjoyed it, and we'll be back tomorrow with. Let's see what we're going to talk about tomorrow. Intermolecular attractions. All right. But we'll be back with that soon. Really quick, with the coronavirus going forward, I just encourage you guys, don't be fearful, but be wise in your decisions, all right? Take precautions. Try to avoid handshakes, hugs, any kisses on the cheeks. I've been doing this whole, hey, what's up, man? All right, so try to do those things. Stay safe. And, yeah, boys out, and I will catch you guys later. All right, so peace.